In this video, we're going to talk about sensors. Sensors are very important to embedded systems, so let's see what kind of sensors we might encounter. Temperature sensors. Temperature sensors make sense to us, okay? We use them every time we take our temperature. In the COVID-19 environment, we're using one of the kinds we're going to talk about right here. First, there's contact sensors. That's a thermometer, okay? It can be thermocouples, thermistors. I think I've got that one on here too. Yep. Resistance temperature detectors. They're mostly made out of platinum. They're very accurate, but they're pretty expensive, okay? And they measure the resistance as the temperature changes across the metal, typically platinum, okay? But all of these are good examples of contact temperature sensors, right? It's either going to be, like I said, the resistance changes or the fluid in the thermometer rises because it expands because of its heat change, but they require contact. Non-contact are temperature sensors like infrared, okay? The kind of thermometer that they shoot at your forehead when you want to go into certain places now and they want to make sure that you don't have a temperature and you're not suffering from COVID-19, okay? Those are non-contact. Why? Because they don't want to put a thermometer in your mouth if you have COVID-19 and nobody knows it, and then take it out and try to clean it and put it in somebody else's. Ew, right? So they're going to hit your forehead or your cheek or your temple, and they're going to read your temperature using infrared. Okay? There's also FLIR, forward-looking infrared. Okay? That's a type of sensor. We use those in the military. Again, it's another infrared. There's just all kinds of systems for reading thermal heat signatures, okay? Distance is another one, okay? It's very good to know, is my automated car about to run into a wall? Is my robot going to walk so far that it walks onto the street and gets hit by a bus, okay? So they're also known as proximity sensors, all right? How far am I from the wall? How far am I from another object that I may be following or may be following me? Okay, and these are very important when we get into self-driving cars. All right, they typically output some sort of a signal, some sort of a wave. It's either IR, it can be ultrasound, it can be radar, it can be LiDAR, but there's some sort of a wave going out. It's going to bounce off whatever it hits and come back. And the sensor is going to tell based on what comes back or when it comes back, what it sees, okay? So it's going to measure the changes in the return signal. That's the kind of the generic way to say it. Now, the resolution is how small of a change can I see? So if you're standing on a skateboard across the room and you start skating towards me, you start rolling towards me on a skateboard, if I can only pick up your distance changes every 5 feet, that's not good resolution. But if I can kind of sense the board wiggling as you're getting ready to push off, because I can see those tiny little motions before you actually roll forward, that's really good resistance, okay? Resolution. So the resolution is how small of a change can I detect? If I'm a police officer aiming at your car, can I tell that you're going 55.2 miles an hour, or I can only tell that you're doing between 50 and 52. Okay, how accurate is the measurement that I can detect the change? Okay, and that's going to have a lot to do with the algorithms of how it processes. All right, the update rate. This is how fast am I reading those waves or that return signal, right? Because I may have good resolution, but I'm not reading it fast enough. Maybe I'm in a downgraded mode, or I'm reading it really fast and I've got good resolution, so I can tell if you think about coming towards me. It's so accurate, okay? So the resolution and the update rate together determine really overall how well that sensor is going to work. And when we talk about the range of a sensor, it's if I can only read you coming at me when you're within 40 feet, I don't have a very good sensor, or I have a limited range sensor. And sometimes you can get too close to where I can no longer read what you're doing. In a system, for example, where certain types of radar and things like that, you may get too close to where the signal to noise ratio doesn't give me a clean return. It's too fast, okay? So I need you out there a little bit. So maybe my range for whatever my distance sensor is from 150 miles down to 1. And inside a mile, I'm not going to read it that accurate, okay? Or maybe it's really good all the way up to 10 feet, but it can only go out to 50 feet, okay? So that's what we talk about, and that's kind of obvious when we deal with the range, okay? Now, light sensing. Light sensing is measuring luminosity intensity, okay? And there's a couple terms with that. A candela is a unit, and it literally comes from a candle. So one candle burning is basically a candela, unit of light, okay? And the lumens is the total luminous flux of a bulb, okay? And that is the candelas of the light times the solid angle that the beam fills. And the solid angle of the beam is measured in steradians, okay, which you may not have heard of. But if a bulb is sitting by itself and it's just lighting everything around it and there's nothing in its way, that's basically 4 pi steradians. So if it's shining in half the direction because there's a mirror behind it and it's focusing the light like in a flashlight, that's 2 pi steradians. But you multiply that times the solid angle that the beam fills, and your lumens is going to be the same. Even though you may shape the light, it's still putting out the same lumens. Okay? Lux is what sensors read, and it's a little bit different because it's light hitting the sensor based on 1 lumen per square meter is what the lux reading is going to be. It's kind of getting the illuminance, and it's doing it through what's called a photodiode. So when the light energy hits this thing, it induces a measurable current. Okay, and then that, from all the current that is induced, that tells me how much light I'm getting, and that sensor is a photodiode, aka a solar panel. Okay, a solar panel is just a big photodiode, okay, that instead of measuring how much light it's hitting, it's taking that current and turning it into stored energy. Okay? Photoresistors measure the change, as the change in light drives a change in the resistance on the sensor, okay? It can measure the change. It's not real accurate, but it's real easy to do and it's very cheap, okay? So photoresistors can give you relative light. So you're in your car and you're driving, it's night. And somehow your car, the newer cars, can tell it's getting dark outside. It's dusk. And all of a sudden your dashboard lights go dim. Or you've been driving all night and it's light and the rising sun's in your eye, and all of a sudden your dashboard lights go bright so you can read them again. That's because of a photoresistor light sensor on your dashboard that's very inexpensive to put in there, that can tell your car, hey, it's light out. Oh, it's dark. Okay? Your cell phone does it. Your cell phone can auto dim based on the lighting conditions. Okay? So that's all that is. It's not as accurate, right? It's going to tell you lights on, lights off, or some relative chunks of light are present, but it's really easy to do and it's very low cost. Okay? Sound. Sound is basically sensing it like your ears, okay? Like human speech. All right? It's related to the human ear, and it's basically through a microphone. Okay? The microphone's going to deflect. There's going to be a current. It trips the sensor. Hey, sound is occurring. Okay? But it's basically a microphone. And if the microphone is aimed in a security system that can tell, ooh, a little mouse just walked into the room that the Mona Lisa's in. Somebody sent a security guard to trap it. Oh, turns out that's a crook, right? Trying to steal the painting. So sound can be used as a sensor, okay? But it's basically a microphone that is creating the current because of the movement on the diaphragm of the microphone. And it's basically, you know, the magnets are, there's a current that's occurring, and so it senses it and sets off whatever the alert is. Okay, now, contact. Contact sensors tell if two things are touching. One of the most common ones you're going to see is there's something on one and something on the other, and they're together. And when you move them apart, that circuit is opened or closed. It's opened, and oh, look, we're not touching. Okay? So that's basically the simple one. When the pieces move apart, the sensor opens, and it tells them they're not touching. Okay? Now pressure. There's all kinds of pressure. Pressure can measure air, liquids, right? It can any gas and any liquid. You can measure the pressure. Okay? All kinds of uses for pressure sensors. Absolute ones compare the pressure they're reading against a perfect vacuum. Okay? That's why it's called absolute. A gauge is relative to atmospheric pressure. Okay? My altimeter is a gauge that tells me the reference to the atmospheric pressure when I take off. It's not quite the same, but it's kind of a good analogy to kind of get you started on this. A vacuum pressure gauge measures pressures below atmospheric pressure. So if it's a vacuum, it's below atmospheric pressure. A gauge is relative. It can be above or below, but basically a gauge pressure valve is reading it relative to the whatever the atmospheric pressure is. So if I have a gauge valve in here, it's going to read the pressure in this room, and then whatever it's reading that it's sensing is going to be based on a relative pressure to this. Okay? Differential is I'm connected to two different pressures, and I'm going to tell you the difference, whether this one's higher or this one's higher. That's all it is. Sealed is like a gauge, well, it's relative, but it's measured against some other fixed pressure. So if I'm in a chamber of some device and it's always going to be at 1,000 psi, and I want to know what this other pressure is relative to that fixed 1,000 psi, that's what it's telling me. Okay, so that's sealed. Think of it as like a sealed system where this is always going to be 1,000 psi. So I need to know what the difference is over here. Okay, couple more, and these are really kind of how it's done. You've got a piezo-resistive. I'm never going to say that right. Strain, which means there's some device that's being bent because of the pressure, and it's reading the strain, okay, to tell you what the pressure is. All right, capacitive is basically the deflection of a diaphragm against some sort of an air cavity, typically. Okay, so as much as it bends against that cavity, it's going to tell you the pressure. Electromagnetic is another diaphragm deflection, but the induction of the deflection is measured, so you get an electrical measurement of that on the diaphragm. Piezoelectric is only dynamic pressures, so it can't tell you the static pressure of a water tank. But if the pressure is constantly changing, excuse me, it can tell the directional change or the relative change of the pressure to what it is at any given time. Okay? So it's measuring strain on the system, but it can only do dynamic pressures. Optical. There's literally an optical fiber in an optical system, and it's going to deflect or be deformed based on the pressure, and that's what it's reading. There's three others that I'm really not going to go into much. There's a resonant, which measures resonating frequency. There's thermal, which is a pressure gauge, but it's testing the thermal conductivity to interpret the pressure. And then there's ionization, which is the flow of gas particles if you're measuring a gas pressure. And that's really beyond the scope of what we need to do. Now, where do we use pressure? Altimeters. Every time I went flying, I set the local pressure altimeter, and the needle should read what my field elevation is. So if I'm on a field near the ocean, it might be 60 feet. Okay? I go flying, okay, and if I'm below the air routes, I'm going to be on that local altimeter setting. And when I fly across the country, the different radar stations are going to give me their local altimeter in case I need to do an emergency landing. If I'm on the airways, I reset it to 2992, and everybody is standardized because we're high enough we're not going to fly into the ground. And I want to know that I'm actually at 10,000 feet mean sea level, and this guy's at 12, we're not going to run into each other. When I come down to land, I need the local altimeter setting so that I know where I am above the ground. And the altimeter is reading the pressure altitude that I'm at. Same thing if you're a diver. When I went diving with my son, we had to know how deep we were because we had to know how much we needed to stop at different stages so that we came up safely and slow enough. And we needed to know how long we were at certain pressure depths, okay? So that was very important to have a good pressure gauge on our system. Weather instruments, okay? During the thunderstorm that I think it's past now, my phone cooked off, my watch cooked off 4 times warning me that the local pressure was dropping to expect a storm. Now, it's not real fast because I was already hearing the thunder, but somewhere there's a weather station in Georgia that picked up the pressure dropping, which set off a signal that recorded the pressure change on the internet somewhere, where my service through my watch said, hey, we need to tell him there might be a storm. That's pretty cool. And that is absolutely an embedded system connected to the cloud, which is providing me casual information that, hey, there might be a storm nearby. I mean, how cool is that? Okay? And that thing is sitting in a low power network somewhere, just reading the pressure, and, oh, look, it changed. Let me report that. Okay? Or maybe every 5 minutes, it's repeating the local pressure, and it's being collected and analyzed through a system that actually puts reports out. Okay? So weather instruments is a big deal. Flow sensing. The dam at Lake Lanier. They need to know how much water is flowing under that dam. They control the waterways and the water supply, and if above the lake it's getting too full, they can let water pressure out if we're getting a lot of rain. They need to know how that water's flowing. So when they move a valve, they better see water flow or something's wrong with the system. Okay? Level and depth sensors. We talked about that as a diver. If you're running a submarine, you need to know the pressure depth of that submarine. Leak testing. People don't think about this one, but I like it because I used to fly aircraft with 3,000 psi systems. And the pressure of the system can tell me if it's leaking. And I had these analog gauges that would pop up sideways like this, pointing opposite each other, 2 needles. Okay? My 2 pumps. Right? And if they started doing this and dropping, I was losing pressure. Well, there was only one way I would lose pressure. If it was leaking. Okay? And leaking hydraulics in an aircraft is not good. So you really want to know that your hydraulics are leaking if they're leaking. Okay? I even flew a rescue mission for a Hawkeye that had to spiral down into Chicago because one of their systems did that and they barely made it on deck, and when they rolled out into the arresting gear, their other system failed. And it was those pressure valves used as leak detectors that literally saved their lives. Okay? That's a good example. All right. So, position sensors can use GPS. They come in many flavors. And they can use, and if it's GPS, it's called an absolute position. Where are you on the earth? Okay? And airplanes use those every day. Hikers use them, okay? Our watches have GPS position. Our cell phones have GPS, okay? Our cameras can record the GPS position. By the way, that's a security threat. If you have pictures of little kids that you put on the internet, you need to strip the XML GPS because that is a predator threat, okay? People don't think about that. They just put pictures of their kids all over social media. Okay? And there are predators out there who read the lat long where that picture was taken. So be careful with that. But absolute position is where are we on the planet. Proximity is how close am I to something else. All right? Relative position. Are we both moving towards each other? We're both moving, or are we moving apart? Relative position is going to be very important with self-driving cars and self-flying quadcopter taxis as we invent those, okay? Your relative position can change and it can be very dynamic. So you need sensors that have a high degree of accuracy of where I am relative to this guy, okay? Especially if we have drones that want to fly formation, okay? You need to know that you're maintaining, 6-8 feet of separation. All right. Encoders. Absolute, they can be optical or mechanical, okay? So I can have an encoder that tells me where I'm at and moves me to another spot or has the control signaling to do that. And it can be optical or mechanical to tell me where I am or where my proximity is. It can be incremental, okay? So I can have something that moves so accurately that I have 10,000 counts for one revolution of a gear, okay? Or a shaft. All right, so they can be incremental or they can just be on or off. They can be linear. There's straight line relative measuring. So I'm 10 feet away, I'm 12 feet away, now I'm 14 feet away. Okay, so your position can be rotational or it can be linear. All right, so rotary is the rotational I'm obviously talking about. I've turned 20 degrees, or I've turned 20 degrees on heading. Okay, there's lots of ways in 3D that we can talk about rotational differences as well as linear distances. Okay, so that's really kind of just a blow through on sensors, kind of what they are, what they do, and a little bit about how they work. Okay, we kept it at a very high level because we're going to play with some sensors and you'll get to know them a little bit better in the lab. The next discussion we're going to have is on the different types of motors. And I will see you with that on the other side.